Good morning. Assalamualaikum. Where's the rest? They have class before this. Okay, now we start. We continue on step 3. Yesterday we had done until step 2. Input-output structure of the process. What is step 1? We have 5 steps. We are done step 1, step 2. Step 1, still remember what is it? Step 1? Identify whether your process batch or continuous. Step 1. Okay, batch versus continuous. Which one is suitable to your process and power plant? Step 2 is the input-output structure. Identify what is your feed product. Okay. Now we go to step 3. Okay, we go to step 3, the recycle structure of the process. Okay, we know that raw materials are very valuable. Even though you use waste, it's still valuable because there are costs need to be borne. Even though waste you assume free, no need to purchase. Okay, if you assume no need to purchase since it's a waste, but you need to consider the logistic cost, the labor cost. Okay, because you will be using a lot of amount of the raw material, even though it is a waste. You still need to consider the labor cost, transporting cost. Okay. And then the raw materials, they make up between 10% to 50% of the total operating cost. Separation and recycling of unused reactants is therefore very important. Okay, so let's say after your process, you have products over here. Okay, products, but then you still has unreacted raw materials, which you can recycle. Okay, exception is when raw materials are very cheap. If you consider your raw material very cheap, perhaps you can have the source of material is very abundant and very cheap. Then you can consider not to recycle, because recycle stream also take up a lot of cost as well. The piping, the instrument, everything. Okay. Then extent of recycling of unused reactant depends on the ease of separation. Okay, depends on the ease of separation. Meaning that here, once the outlet stream over here, you have product and reactant. So you need to check, is it easy to split between the unreacted and the product? If it is not easy, then consider no recycling. Okay, do not recycle. There are few cases later on you will see. Okay. If it is easy to split, then consider to recycle. If it is not, no need to recycle. Or perhaps you can treat or purify your product. Okay. Efficiency of the raw material usage, you can use a single pass conversion in the reactor. Okay, the overall conversion in the process and also the yield. This will monitor you the efficiency of the raw material usage. The yield, how many percent of the yield? Perhaps your process is high efficient, so you can have, let's say, 90% yield. Okay, so 90% yield, then perhaps the 10% you want to recycle. Check back whether it is worth it to recycle or not. Okay. Now, this is the recycle structure of the process. There are three cases, three general cases. Okay, if you read through journals or articles, perhaps they have more than this. Okay, as the recycle stream increase, equipment and operating costs also increase. Okay, that's why you need to do the calculation wisely. So there are three cases over here. The simplest would be, okay, this one. Separate and purify unreacted feed material from products, then recycle. Okay, so you just separate and purify. Okay, this one, as per previous slide, you have product, you have feed. Then you separate and recycle the unreacted reactant. Then purify your products. Okay, this one is the simplest. But again, it depends to the composition of the outlet stream. Okay. Now, for this case, you need to consider the suitable unit of. Let me make it bigger. Okay, suitable unit operations. Maybe here you just need to purify using evaporator, perhaps. Then you just split your product and the water, the steam. Okay. Recycle back the steam into the feed, for example. Okay. Now, second method is, okay, go this one. Recycle feed and product together and use a purge stream. Okay, here, let's say you have product, feed. Okay, you split the feed. Okay, recycle feed and product. Feed and product. Feed and product. And use a purge stream. Purge stream. Okay, wait, I draw it on top. Feed plus product. Okay, here perhaps the separation, the product cannot be fully separated. So have some of the product left. Okay, so purge stream here, you put one purge stream. Okay, why you need the purge over here? Because, yeah, not the blue color one. Let me make it bigger. For the case when a product is recycled with an unused reactant, the product does not react. Okay, then a purge stream must be used to avoid the accumulation. So meaning that when you recycle, the recycle stream contains feed and product. This product, it is not reacting it is, how to say, it cannot be used inside the process, so it won't react. So that's why we need a purge stream, so that this product, when you keep on recycling, it will accumulate. We just need the feed to be recycled. So the product will keep accumulating. So that's why we need a purge stream to purge out the accumulated product. Okay? Yeah? Next question. First one just now, we just separate the feed and the product straight away. Purify the product and recycle the feed only. Second case, where you recycle both feed and product, but you need to have a purge stream to purge out the product. Why we need to purge out the product or take out the product? Because the product will keep accumulating. It is not involved in the process. We just need the feeds. Okay. Now, third case, recycle feed and product together and do not use a purge stream. Okay, when to use this? This recycle scheme is feasible only when the product can react further in the reactor. Okay, and therefore there is no need to purge it from the process. So meaning that when you have product, okay, feed, recycle feed plus the product. No need to purge the product out because the product involved in the reaction. It can involve in the reaction. So you don't need to purge out the product. Okay. And so there are three cases over here, three main cases. You need to consider which one is suitable for your plant. Okay, now I give you this adapted from journals. Wait, I make it the diagram bigger. Adapted from the journals. It is a reduction of gas emission. Let me make it larger. Okay, this is the title of the journals. Reduction of gas emission via optimization of purified purged gas. Recycle ratio for conversion of CO2 to methanol. So what is the feed over here? Identify the feed and product first. What is the feed? Huh? From the title itself, what is the feed? From the title, what is the feed? Huh? Yes, what is the fresh feed? CO2, yes. From the title, you can see here, conversion of CO2 to methanol. One of the feed is CO2. Okay, the focus here, they want to recycle the CO2. Reduction of gas emission, okay, via optimization of purified purge gas recycle ratio for conversion of CO2 to methanol. Okay, it starts from here. This is the main reactor. Okay, this is the reactor. This is this one also the first reactor. This is the second reactor. Okay, you see, yeah, over here. Where is the first inlet stream? Where is the first inlet stream? Fresh feed, you have two fresh feed over here. This fresh feed, this fresh feed. Huh? The bottom one. Okay, the bottom one, fresh feed. Before there is a recycle system, this is the first influent stream. Okay. Wait. Okay, before the recycle stream, this is the fresh feed before. This is the feed of the fresh feed. Influent before the recycle. Okay, then the fresh feed go into this reactor, pass through, then it must go to this reactor, okay, to react with the catalyst. Then go into the gas cool reactor. Then only it comes out the product. Okay, so you go to purification process, methanol purification process. Here you have the main product, crude methanol. Now, it has a recycle stream over here. Two recycle stream. One go up to here, where the final product would be flare gas. Okay, another one straight away go to the membrane. Okay, there are two recycle stream over here. What is the composition of the recycle stream? Composition of the recycle stream. Here is methanol. Okay, here is the purge gas. You see here, H2. Okay, it goes to the first membrane. One stream goes to this membrane, separate the H2. Then it enters the second membrane. Okay, where it separates the N2. Okay, so perhaps here, over here, the recycle ratio over here, maybe you have N2. So here it separates the N2 from the stream where it formed the NH2. Okay, then it produced the fresh feed to the reactor. Okay, the purge gas of this process include, here it mentioned, hydrogen, CO, CO2, and nitrogen, and also the methane. Okay, so purge gas over here. Purge gas over here. So you have hydrogen, CO, CO2, N2, and also methane. Okay, so flare gas over here. You see the outlet stream from this membrane is only H2. Here it notes as only H2. So the rest of this being flat. What is the flammable gas over here that it use flare? That it decide to use flare. What are the flammable gases? Sorry, what is the flammable gases? Huh? And methane. Yes, methane. This outlet, it has methane. That's why they decide to use flare system. Okay. Note that they also have CO2. CO2 they need for the reaction. CO, is it flammable or inert? Or unflammable? Flammable. Not flammable. Okay, so then try to think it. Okay, then remove the H2. Main concern over here is make H2. Move to the next membrane. Okay, two stage of membrane filter. Here, purge gas that enters directly to the second membrane consists of N2. Okay, because here it mentioned, see here, nitrogen is separated from the recycled gas stream by a novel metallic membrane. This one. Nitrogen is converted to ammonia during the purification process. So here it has N2. Okay. Now my question is, from the three separation method just now, this one. Okay. We have three cases over here. Which cases meet this process on the recycle stream? Again, my question. From the three cases over here, separate recycle structure, from the three cases, which best describe in this process? Second one. Why do you say so? Cycle, fit, and purge. Purge what? This one use purge stream to purge the product. Okay, let's see. Here it purge feed and the byproduct. Right? Yes, we can consider this as the second case because to avoid the accumulation. Other than that, any other options? First one. Why do you say first one? Can the first case be considered? Can. Why do you say so? Why do you think? Can, because here you see the methanol purification process over here. Okay, here is separated the product and the feed. Feed, which is the CO2 H2. Okay, this one is the product. I cannot draw. Okay, here is the product. Yeah, the crude methanol is the product. This stream consists of the feed, which is the H2, the CO2. Okay, it still can consider on the first case because here it mentioned the methanol purification process. So it must have a specific unit of over here to separate the product and also the feed, unreacted reactant. Okay, it is not limited to one method. You can combine or it can be any of the methods. Okay, there is no right or wrong to use only one method or use both methods. It depends to the complexity of your process. Okay, that's why I want you to understand the concept, not only memorize the answer. Okay, so like this case, I give you one case study. You should know which recycle system to be chosen and why. Okay. Engineers is problem solver. You must have critical thinking skill. Not always ask ChatGPT what to do. Okay? You are the engineer, not the ChatGPT. Okay, can? Okay, so these are few factors that you need to consider whether to recycle or not. These are the affecting factors. The uses of excess reactant, okay, recycling of inert materials, and control of an equilibrium reaction. Okay, I'll just go through quickly on the points. How many potential recycle streams? So how many can you do recycle stream? Is it feasible or not? How does excess reactant affect the recycle structure? Okay, how many reactors required? So how do the unreacted raw material stream need to be purified? Okay, is recycling an inert warranted or not? Okay, do you need inert to be recycled? Okay, and what phase is the recycle stream? If you need to change phase, then you need to install the heat exchanger. Again, it is a cost. Okay. Okay, so this is the example of the recycle process of cycle stream. Okay. Any question for the recycle structure? Now we move to step 4, the separation system. Separation. Okay. So the goal of the separator is to produce a product of acceptable purity. Recycle stream of unreacted feed materials and separate the product stream with streams of byproduct. Separation. Okay, separator. There is no reaction involved over here. Separator. The minimum number of simple separation unit must be determined. Simple separation units. Perhaps you need a filter cake to separate the water and the solid, the sludge. Okay, perhaps you need evaporator to remove out the water in your mixture. Okay. The question concerning the separation section. What types of unit should be used? And how should the unit be sequenced? If you need a few distillation column, how should you arrange the distillation column? Okay, how should you arrange what are the components to be separated first? Okay, if it involves multi-component. Okay, this one we will see on the next topic. We'll go into detail on the how to calculate this. Okay. Now, these are the guidelines that you need to understand. Usually we focus on the distillation. Okay, first thing, but this is not, how to say, this is just a guideline. Not compulsory, need to follow step by step guideline. Okay. Remove the largest product stream first. Okay, that is easier. Let's say you have your composition A, B, C. A, you have, let's say 90%. B, 5%. C, 5%. Okay, remove the largest product stream first. A is suggested to be removed first. Okay, because you need the first separator quite a big design because you have larger amount to be removed, to be separate. Okay, so that one, this statement mentioned, this makes all of the subsequent separation units smaller. So from there, perhaps the first distillation column, you need a few, you need quite high volume and high distillation column. Okay, then perhaps after that, just a small one. Okay, then for distillation, remove the product with the highest heat of vaporization first. Highest heat of vaporization first, if possible. Okay, if possible. This reduces the heating and cooling duties for subsequent unit. For distillation column, on the feed component, you must know the properties of the components, like the boiling point, volatility, then the volatile ratio. Okay. Okay, do not recombine separated stream. You already separate, so don't recombine them. If not, you need to separate again. Okay. Do the easy separation first. Do not waste raw materials and do not over purify streams based on their uses. Okay, let's say you just need your final product is purity around 65, should be enough. Meet the market demand already, 65%. You don't simply set up a separation system that purify your product up to 95%, because it will just be a waste. Market only need 65%. So you don't need to further purify up to 95. Okay, it depends your market demand as well. Then remove hazardous or corrosive material first. Use less expensive through the separation technique first. Okay, for example, liquid-liquid extraction before the chromatography. Okay, so these are only the guidelines, which you should know when to use it. Okay, again, the guideline. Choosing separation unit. This one just now guideline for sequencing separation unit. Sequence. You arrange which to be separated first. Okay. This one, guideline to choose which separation unit. Whether distillation comes first or evaporator comes first or other gas separator comes first. Okay, it depends. So use distillation as a first choice for separation of fluids when purity of both product is required. Okay. If you need higher purity, distillation should be considered. Use gas adsorption to remove one trace component from a gas stream. Okay, consider adsorption to remove trace impurities from gas or liquid stream. Adsorption, remove trace of impurities. Okay, this one works with gas and liquid. Consider pressure swing adsorption to purify gas stream. Okay, especially when one of the component has a cryogenic boiling point. Okay. Now consider membranes to separate gases of cryogenic boiling point and relatively low flow rates. Membranes. Okay, choose an alternative to distillation if the boiling points are very close. If the heats of vaporization are high. Okay, but boiling point are very close. Perhaps you need to choose. You need to design few distillation that has many stages. Okay, consider extraction as a choice to purify a liquid from another liquid. Liquid-liquid extraction. Okay, you can consider few types of solvent. Use crystallization to separate two solids or to purify a solid from a liquid solution. Crystallization. Okay. Now this one you can read through the continue of how to choose the separation unit. There are many more consideration. Okay. Now we move to heat exchanger network and process energy recovery. Okay, the main objective is to optimize the energy that a process exchanges with the utilities. Okay, to optimize. At the expense of capital investment, okay, the utility usage can be decreased by exchanging energy between process streams. Amount of energy integration. Okay, function of the relative cost of the utility. Okay, so the process may become more complex and more difficult to control. all involve the cost. Okay. Capital cost involve on how many heat exchanger that you need to install. That one involve the capital cost. Utility cost comes in when you need to consider how much of the water or steam that you need to use. Okay, or refrigerant, electricity. Okay, so this is example of heat integration. For example, this is without heat integration. Okay, this reactor, the inlet should be at 250 degrees C. Outlet 364. Okay, the effluent. The feed, perhaps from your starting stream, is 154 from your supply. You need to heat it up until 250. Okay, you need here one heat exchanger. Now, the effluent at high temperatures need to cool down up to 100 using cooling water. They integrate. Okay, here, let's see how it integrates. Since we know that the inlet need to be at high temperature. So the original feed supply, which is at 154, pass through the heat exchanger, which consider the outlet stream. Okay, here this is the outlet, pass through this heat exchanger, which heat up the inlet feed. Okay, this is at high temperature, pass through the heat exchanger, which heat up the inlet stream. So it can heat up to 250. Later on, you need to calculate how much energy that you need to supply so that this stream reach 250. Okay. Then here the outlet stream, once it in contact with low temperature stream, the temperature will be reduced to 278. Okay. But it is still not approaching the target temperature, which is 100. So here you need to supply one heat exchanger. But you can see over here, the delta T is not big compared to without the heat integration. Okay, delta T over here, 364 minus 100. Delta T still high. Here, delta T already low. Okay. Okay, so meaning that here, you need to find out how much energy that you need to supply so that to meet the target temperature, 100, from 278 to 100. Lower heat required with the heat integration compared to without the heat integration. Okay. Can I? Still, okay, compare without and with, still you need two heat exchanger. Still you need two heat exchanger. E2O2, 2O3 still exists in with heat integration. But the heat supply perhaps will reduce compared to without heat integration. Okay. Ken, any question? Okay, this is an example also, the proposed heat exchanger network showing interior heat exchanger 1 and 3 and heat utilities. Okay, heat exchanger 1, 2, and 3. How they combine the stream to supply the heat to each other. Okay, so here it needs two, sorry, here is the heat exchanger, H, heating and cooling. 2 for heating, 1 for cooling. Heat exchanger network. Okay, here they combine T2 stream from 180 need to be heated up to 232. Sorry, need to be heated up to 240. Okay, but from the heat exchanger network, it can heat up the stream up to 232. Then you need to supply extra heat exchanger to meet the target temperature. Okay, 240. This is the target temperature. Instead, you use one sole heat exchanger heating from 180 to 240. Okay, from 180 to 240. Sorry, Fahrenheit. Okay, you need one heat exchanger where here the delta T is high. Compare if you do the heat exchanger network. Okay, supply the hot stream from H over here pass through the C2. Somehow it will heat up a bit the stream. So here you will need to heat up temperature from 232 sorry 2232 up to 240. So here delta T is low compared to this. So here later on delta H is also low. Okay, less energy required to heat up the targeted stream to targeted temperature. Okay. In chapter 4, we will do in details the heat exchanger network. Okay. Now this one you should know how to do it so that you can incorporate in your PDP. PDP 1 up to heat exchanger, right? Sorry, heat integration, right? Okay. Any questions so far? Now this one it differentiate what involved in your capital costs and the operating costs. Okay, capital cost mainly on the equipments, unit operation. Okay, for the onion model, you can see over here, onion model, we start from the inside, from the reactor, then goes up until the utilities. Okay, we see how it considered. First layer, the reactor. Once you have gone through the part 1 and part 2, you develop your base case, you have the process flow already, and then you go through the detailed design. Okay, then you identify your reactor. What reactor need to be used? Okay, once the reactor is decided, design the separation system. You must know the reaction occur first. Okay, remember the first step last time, we need to know what are the reaction involved to produce your product. That is the first part, reaction. So in that reaction, what reactor involved? What type of reactor? How many reactor involved? Then from the reactor, you have your product. So the product, the effluent from the reactor contains a mixture of product or unreacted reactant. Then how to separate it? Okay, then that's when the second layer comes in, the separator. First reactor, second separator. Okay, then once the reactor and separation system identified, you need to proceed with the heat exchanger network. Okay, heat exchanger network. Because reactor, you must have your certain condition, perhaps at high temperature. So the effluent stream must be at high temperature. So try to consider whether you can do any heat integration over here. Then the separator. For example, you use a distillation column. Okay, the hot stream from the bottom product can be used as for the heat integration as well. Okay, this one at high temperature. So it can be used to perhaps heat up the feed stream. Okay. Third layer is the heat exchanger network. Fourth layer comes the utilities. Okay, so once you finalize your heat exchanger networks, you already identify how many heat exchanger do you need to install. Then only you decide how the amount of the utilities, how much cooling water you need to supply, how much steam that you need to supply. Okay. And okay, this one you can see through how they transfer the utilities and then involve the water management. When everything decided, then it complete the onion models. Okay. Now we go through one example. I think enough time for one example only. Now here, there are two technically viable routes to the production of hydrocarbon solvent S. This is your product. S is your product. Starting with feed material A. A is your feed. S is your product. Now, root 1 uses a proportionation. Okay. Root 1 use this method in which feed material A is converted to the desired solvent S and another solvent R. Okay, root 1. This is the feed. This is the main product. R is the byproduct. Okay. Both products are marketable. Then root 2 starts with the same chemical A, but uses this method to produce the desired solvent. Desired solvent here means the S. Okay, so the reaction scheme for each process are shown below. There are two possible routes to produce the S. Now, assuming that pure A is fed to the process, the solvents S and R are separable by simple distillation. And both are much less volatile than either methane or hydrogen. Much less volatile than either methane or hydrogen. Okay, in terms of volatility, okay, we assume this. H2 and CH4 is more volatile compared to the S and R. S and R are separable by simple distillation. Simple distillation. So meaning that you don't need plates. Perhaps you just need a few plates. Simple distillation. Top product, bottom product. That's it, right? So from that statement, what can you extract the info? S and R are separable by simple distillation. So S and R, the delta T is quite high. The difference of the boiling point is high. Difference in boiling point. So perhaps, for example, this one is just for example. Maybe S has boiling point 200 degrees C. So R has boiling point perhaps 70. Okay, the gap is big. That's why it is separable by simple distillation only. So from here, it doesn't mention which one is top and bottom product. You can assume on your own. So let's say this is my assumption. So the S will be top or bottom product. Bottom. S will be bottom product. R will be top product. Okay, this one fits the description of S and R are separable by simple distillation. Now, the question asks you to sketch PFDs for root 1 and root 2. Meaning that from the statement over here, you should sketch from the reaction process then involve the separation process. Sorry, not R. Reaction, reaction, not the product. So you should draw the PFD involve the reaction and separation for both routes. Then from there, try to conclude which process do you think will be more profitable. Explain your reasoning. Okay, for question number 2, it is not limited. For example, you say route 1. You should explain why you say route 1 is more profitable. If let's say you sketch, then you find out route 2 is more profitable. Explain your reasoning. Okay, that's right. Okay, I give you a few minutes to digest and try to sketch how it looks like. Sketch the PFD. The BFD lah, the block flow diagram. Okay, try. Okay, let's try. We discuss. For root 1, the reaction occurs is 2A, sorry, 2, S plus R. Okay, we go through one by one. Now here your feed is only A. Okay, feed is only A. So reactor, your feed A. Then you have product S plus R. Okay, we need to separate the S and R. So here you can consider using distillation column. Simple distillation column. Okay, you already mentioned. So since the question doesn't mention which one is top and bottom, from the assumption just now, which product will be top and bottom? Huh? R top, S bottom. Okay, this is root 1. Done. We have your BFD. Okay. Now for root 2, any other, okay, for root 1, any other possible consideration? That's all that you can think. Here, where? To separate what?
And recycle
S and R. Here we already separate S and R. The second separator where? To separate again S and R.
and then recycle the
Recycle the A, meaning that you say the unreacted. Okay, if you assume there is unreacted, you can consider to recycle. Yes, can. But then you need to add on more separator. Okay, and need to assume the boiling point of the A. Okay. Now for B, root 2, we have this reaction. Now your feed is, this one is reactor. The feed is A plus H2. Okay, your product over here is S and CH4. Okay, then two-phase what? Two-phase separator. Why do you need two-phase separator? Huh? One gas and one liquid. Okay. Make your description. You assume S is liquid. And not assume, you already mentioned, right? Is it liquid? Solvent. Solvent, liquid. Okay, can? So here the output will be CH4 and S. Okay. So now, from these two, which one you think is more feasible? This is the simplest version of the root. Now, represent the root. If you consider the H2 and A in the product stream, then you need to do another separation, split them, and recycle back. Okay. Now, from these two, which one is more feasible? Second one. Why do you think second one? There's no right or wrong over here. It depends to your justification. Why do you think second one? We Reduce the separating cost by using the two-phase separator instead of distillation column. Okay, that's one point. First one, why do you think first one?
We use things of A. You can sell one.
Correct? Acceptable? One rectangle. Okay, if root one, you have only one rectangle, which is the A. If root two, you have two rectangles. Okay, A and H. And then for root two, S and R is marketables. Can be sold, correct? Can? And then this one, S and methane also marketable. Marketable. Okay. Then this one use two-phase separator. Two-phase separator. This one using distillation column. Simple distillation column. Okay, so it depends how you justify which process is more feasible. There's no right or wrong over here. It's all based on your justification. Okay. Okay, so we are done with chapter 1. Any question? Finally, finish chapter 1. Next, chapter 2 will be more, we will touch on calculation of chapter 2. Theory, some theory and some calculation. Okay, anyone? Okay. So for those who haven't scanned for QR, can do now. Those who cannot scan for QR, write your name over here manually. Okay, that's all. Thank you. I will upload the videos by this week. Okay. Yeah. Oh, your hand ring.